Hi, I'm Limei Wang from Shanxi University. I'm going to present the abstract of our paper. In this paper, the passage of cold cesium 49s Rydberg atoms through an electric field induced volume crossing with nearby hydrogen-like Rydberg levels is employed to prepare a cold dipolar Rydberg atom gas. At the beginning, we trapped the cold cesium atom cloud of the temperature about 100 microkelvin in a standard magnetic optical trap. Then, we used the two-photon excitation to prepare the atom in 49s Rydberg state. The wave function of S state is almost spherically symmetric, like the blue balls. When the electric field is slowly ramped through one selected volume crossing, a small fraction of the 49s state atoms will non-adiabatically stay in an S-like Rydberg state, while the majority of the atoms will adiabatically transfer into high-L Rydberg Sachs states with large electric dipole moment and elongated wave function. Experimentally, we cannot separate these two states because they stay both in low M states and their energies are very close. Their electric field ionization thresholds are almost the same. To separate them and detect this adiabatic transition, we add some holding time, delta T2, during which the field is held at its final value after the passage. During the holding time, the atoms in states with high L but low M have a much bigger chance to become high M states. This is because the high L atoms have large permanent electric dipole moments and interact much more strongly due to M mixing caused by strong electric dipole-dipole interaction. After the M mixing, the atoms in high M state have much higher field ionization threshold. This makes them invisible. As you see here, we can observe a large atom loss when the holding time is changed from 0 to 1 microsecond. The signal loss reflects the departure of high L atoms into undetectable high M states. Do the M mixing collisions really cause the signal loss? We repeat the same experiment at lower densities. We indeed see that at lower atomic densities, the signal loss becomes less significant. We explain this trend by the fact that at lower density, the M mixing collisions are weaker because of smaller electric dipole-dipole interactions. In conclusion, I have shown you two key processes to generate the dipolar Rydberg-atom gas. Firstly, adiabatic transfer of S-state atoms into high L atoms with low M value. Secondly, adding some holding time allows the atoms to become transferred from low M into high M states by M mixing collisions. In our detection method, this is important in discerning adiabatic from diabatic passage. In the future work, one may employ state transformation via adiabatic passage as a method to generate highly dipolar matter against obstacles that may otherwise arise from inhomogeneous broadening, excitation blockade effects, and small rates for direct optical excitation of highly dipolar states. Thanks very much and enjoy the paper.